Modern militaries rely upon remote image sensors for real-time intelligence. A typical remote system consists of an unmanned aerial vehicle, or UAV, with an attached camera. A video stream is sent from the UAV through a bandwidth-constrained satellite connection to an intelligence processing unit. In this research, an upgrade to this remote video stream method of collection is proposed. A UAV in a virtual environment flies around a scene and captures a set of images. The images are sent to a pipeline of computer vision algorithms collectively known as structure from motion. The output of structure from motion, a three-dimensional model, is then assessed as a possible replacement for the images from which it was created. The use of a virtual environment allows for deterministic, repeatable results, saves cost for UAV equipment, saves time during actual experiment runs, and allows modification of the environment to increase or decrease realism, such as lighting, weather, and camera sensor conditions, based on test objectives. This study shows structure from motion results from a modifiable spiral flight path and compares the geoaccuracy of each result. A flattening of height is observed, and an automated compensation for this flattening is proposed and performed. Each reconstruction is also compressed, and the size of the compression is compared with the compressed size of the images from which it was created. A reduction of 49 to 60% of required space, or bandwidth in a network transfer context, is shown. First, a flight path is defined. The basic flight path is a spiral with 3 orbits. The parameters are adjustable by experiment and consist of a ground radius ρ, a starting height z0, a distance between orbits zb, and a horizontal focal length f. Once a flight path is defined, the virtual UAV follows a path capturing 90 evenly spaced images. In this case, the UAV looks at the center point of the scene. The real-world analog to this is a set of latitude, longitude, altitude coordinates. Once the set of 90 images is captured, it is input to a structure from motion pipeline. The pipeline in this experiment utilized the multi-view environment and multi-view stereo texturing tools by the Technical University of Darmstadt and the Poisson reconstruction tool by Pierre Moulin. The tools in the pipeline are multi-threaded but do not currently support graphical processing unit acceleration. The timing and energy required were not rigorously measured, but a typical set required 15 to 25 minutes on a machine with an Intel Xeon E3-1505M processor. When the structure from motion process completes, a three-dimensional reconstruction model is produced, which can be imported back into the virtual world with the true scene for comparison. Before comparison can take place, however, the reconstruction must be aligned by scaling, rotating, and positioning the reconstruction. Care was taken to ensure the reconstructed road was level with the original, and the bases of the building walls of the original and the reconstruction were similarly lined up. With initial alignment complete, it is obvious that the structure from motion process has shortened the height of the original scene. To quantify this shortening, a set of geopoints is chosen for reference and error measurement. In this case, the lower left window corners of the tallest building were chosen as geopoints and marked on both the original building and its reconstruction. The three-dimensional distance from the original building's geopoint to its corresponding geopoint on the reconstruction represents the amount of error in the reconstruction. These distances are arithmetically averaged to provide an overall error metric. To compensate for this warping in the z-dimension, a scale factor is applied in the z-dimension only. To automatically optimize this z-scale, scale factors are attempted in increments of 0.01. At each scale factor, the error metric is calculated. The best z-scale is determined to be the scale at which the error metric is minimized. The optimal z-scale varied from set to set, with values typically ranging from 1.20 to 1.60. In a real-world scenario, this z-scale compensation would not be possible due to a lack of truth data. Instead, a technique involving a range-finding sensor may be acceptable. The UAV would determine the highest point of the scene based on its reconstruction, fly to the real-world location, determine the actual height of the scene at that point, and scale up the reconstruction accordingly. Finally, the reconstructed models and the sets of images from which they were made were compressed with the 7-zip utility. The size of each model and its corresponding set were compared, and in all cases, the model required 49 to 60% less space than the images. This size reduction is favorable in the UAV intelligence application, where satellite bandwidth may be extremely limited. The size of the model may further be reduced by removing the vertices and textures of the road or terrain, which may already be available from previous satellite imagery collection. This research utilized a 3D virtual world to examine the basic feasibility of replacing a video stream with a structure from motion model stream for intelligence gathering purposes. The initial results are generally favorable, showing geoaccuracy to within a few meters after automatic z-axis correction, and potential bandwidth savings of over 50%. However, tests under more realistic conditions must be conducted to more accurately determine the feasibility of this solution.